Hello, everybody, and thank you for attending this live stream about the hype of CO2. We have
Hype.
quite a panel today. We have John Broughton from the UK. Hi, John.
Yeah.
Hi, Jens. Good afternoon,
And
everybody. Good morning.
we have Jamie from Canada. Yep. And we have Christian Braque de la Pierre from France.
Hello.
Good. And Jörg Saar from Germany.
Hello.
Yeah. And myself from Denmark. Hi. Uh, as usual, this live stream is driven by your questions, the audience questions. So please let us have all your nice questions and let us know from where you are actually joining. Um, we'll very much like our experts' brains to get working now. So please go ahead. Let's get some nice questions about this. But before we go on to this, I have a question to the panel, and it goes like this: CO2 is not really anything new, not at all. But maybe in smaller systems. So let me hear from you experts, where do you see the limits for use of CO2 in commercial systems? And what would be the limit? Why would you limit it?
Hmm.
That's
a good one. Who wants to start?
I mean, I can I can take a stab at that a little bit. I mean, I have seen small, 1 meter high kind of coolers in an office environment, and you can tell it's got CO2 in it because it gives you a warning on the maximum temperature that the unit can sit in. And if you look at the cost of CO2 systems, that is probably one of the limiting factors, is that you have to compete on a market where a lot of that on the smaller size systems is price. It's very, very price driven. And so what they're looking at is getting the best performance for the lowest manufacturing cost. So CO2 probably isn't the least expensive refrigerant when it comes to manufacturing these small systems. So I'm sure that may have some kind of limitation, but the fact is it has to also be in a controlled temperature environment. So you couldn't put it in a space where, say, in an outside warehouse where the sun's shining and you're in the southern US, or southern Europe, where the temperature can get 35 degrees Celsius. You could not use it in a place like that because it would be above the temperature that you're allowed to have CO2, and you would either, it would probably end up venting most of the refrigerant that was in the system because of the safety. So I think those are two limitations that I see, personally anyways.
Yeah. Um, I wonder whether there are limitations. I mean, of course, the, there are points where you wonder and where you ask yourself, does it still make sense? From a technical point of view, you could build
Hmm.
very small CO2 systems.
Hmm.
As you say, Jamie, for some of these systems, the big question is, does it make sense?
Hmm.
Or are there other solutions which are more economical, easier to build?
Hmm.
As you said, when it gets really small, so down 2 kilowatts, below 2 kilowatts, that's where I don't see too much CO2 usage.
Hmm.
When we talk about 5, 10, 20, and so on, of course, not every system is CO2, but CO2 can make a lot of sense there.
Hmm.
But if
Hmm.
we go too small, then yeah, then I wonder whether it makes sense.
Well, it's a good point. Somebody made a comment about small systems would be R290. And from a North American standpoint, if you look on a website of a major manufacturer here, like True or somebody, they're all R290. In fact, I remember when R290 was coming in, um, and in North America, we would call these like quarter, half, third, three-quarter horsepower units. Um, if you compare the efficiency of R134A and R290, I mean, you're looking at 20-30% efficiency gains with R290. But aside from that, you also have to look at people's purchasing preferences. there's a lot of hype around R290 as well being flammable, and people don't want to have something flammable in their office. They feel threatened by it. So here's an alternative, CO2. And does it make sense technically? Maybe not, but it is something that somebody may buy for other reasons, as I say, personal reasons or
Don't you think that
fear and misunderstanding.
don't you think that might be also coming from an harmonization point of view? Today we have seen for the very large racks a lot of CO2 installation which have been done. It has been driven by the refrigerant price. You talk
Mhm.
about the price,
Mhm.
but also the technology want to be impacted. And for them, when they have put a choice on the refrigerants, it may feel logic for them to reach that. So you're right, Jorg. There is a limit. 2, 1, 2, 3 kilowatt might be also a limit. Where other system like R290 is a good one also.
Mhm.
But harmonization, yeah, price, yeah.
Yeah, I agree to that. It is, of course, driven a lot by regulations as well. So no matter where we are, we talk about a reduction of greenhouse gases. So Kigali Protocol and all of that. That, of course, pushes towards refrigerants which have a low global warming potential. CO2 has a global warming potential of 1. And that's one of the reasons why we look at that refrigerant. And
Mhm.
as you say, Christian, if we go to certain applications, a supermarket makes a lot of sense
Oh
because
yeah.
we could get rid of 404A with a high global warming potential. And we have advantages like a very nice reuse of the heat.
There you go, right there. That's 100%. I think a lot of what you just said, that's a big part is you have to look at the total energy picture of it. What does it allow you to do?
Mm, yeah,
Right. Now, you guys
exactly.
do a lot of reheat in Europe, much more than we do here.
For
Um,
for
how
larger
big of a
system,
part
yes.
does that play in CO2 over in Europe?
For larger system, yes, they reuse a lot about the heating. For smaller system, sometimes the cost of the piping costs more than what we
Hmm.
can win, or let's say that the payback are
Hmm.
too long, 5, 10 years.
Okay.
That's true. There is a lot of heat recovery here. And if we go back to a supermarket and you build a supermarket of a certain size, then it's pretty normal to have CO2 as a refrigerant. And now it's pretty normal to use the heat coming from your frozen pizza, frozen chicken, and so on, from your chilled milk via the refrigeration system to heat up your supermarket, to heat up the sanitary hot water in your supermarket. So that's standard now, if you want.
Hmm. I think we have a couple of questions here. Regarding CO2 supply chain, is refrigerant grade CO2 readily available, or are these rumors propagated by the enemies of CO2? What do you guys think?
Well, I've heard about CO2 shortages. Yes. Um, there were discussions that in general CO2 was not available for certain applications for some time.
Hmm.
However, that was not a long-term thing, at least not to my knowledge. And in my opinion, refrigerant grade CO2 is available.
Yeah, I would agree, Jorg. The sites that we've worked on, we've had no issues getting refrigerant grade CO2 within Europe, not at all. I don't know what it's like in the US. I think that's where Scott is from.
Yeah, North America.
North America.
Yeah, so yeah, I can't comment on that. But yeah, you've given the answer, Jamie. So
Yeah. I don't understand that there's a lot of issues getting CO2. There isn't as much penetration here into supermarkets in CO2. I'm in Canada, so if you go into Quebec and Ontario and other regions, we do have a relatively good installed base with CO2 systems, but I don't think it's anywhere near the penetration you've seen in Europe. But I personally have not heard of any shortage of CO2 refrigerant grade. That doesn't necessarily mean it doesn't happen or it hasn't happened. The issue it happens to be is, is it COVID related? Is it supply chain related? Because a year ago, you couldn't get anything practically. You couldn't even get room on a ship to put something on without paying exorbitant amounts of money. So it's pretty hard to, disentangle that from any type of specific shortage.
Yeah, I can see we are getting a lot of questions coming in now. That's great. That's perfect. We have one from Jeremiah Perez. Do you have any program for future CO2 heat pumps?
Yeah, not only for future.
Yeah.
So already now, Danfoss provides components to manufacturers of CO2 heat pumps. Those heat pumps we talk about here are typically of larger size, but are dedicated heat pumps, sometimes really, really big. So in the range of several hundred kilowatts, megawatts, where CO2 then is the refrigerant for these heat pumps to provide higher temperatures for district water or district heating networks, for example.
Great, thanks. We have another question from Matt Killis. What do you think about R513A when you compare with CO2 as talking about GWP, ODP, and efficiency?
513, is that the replacement for R134, right?
Yeah.
Yep.
Okay.
Yeah.
It's hard to keep track of these new refrigerants, or I'm just getting old. I don't know which one, but maybe both.
Yeah, I mean, a 513 has got a GWP around about 750, somewhere around there.
Oof. Okay, so it's high.
It's high. It's a low density refrigerant, same as 134A. So it's got a higher GWP than CO2, which is 1, and not as efficient. So I guess that's the comparison.
Yeah, I mean, if you look at, without getting all technical, but if you look at like a pressure enthalpy diagram, if you look at how much heat each kilogram or pound of refrigerant absorbs when it goes into the evaporator and is transferred from a liquid to a vapor, that along with its density plays a big role in the size and power requirements for a system. So CO2 is very efficient when it comes to absorbing heat. In other words, it can absorb a lot more energy than a refrigerant like 404 or 513 can for every pound or kilogram of refrigerant you got to pump. At the same time, it's also got a very high density, which means that for a given mass of refrigerant, it doesn't take up much volume. So R290, on the other hand, is a very low density refrigerant. So you need more volume, but that is offset by the fact that R290 has an incredibly high ability to absorb heat for each pound of refrigerant. It's actually substantially greater than CO2. But at the same time, the issue is it's also a lot less dense. So the physical size of your piping and everything else has to kind of increase. So HFCs and things like that really can't compete when it comes to a lot of the natural refrigerants on efficiency. There's just no comparison whatsoever. So that's really the big lowdown. The only advantage, and they have lower global warming. So all around, these natural refrigerants beat from a physical characteristic any artificial refrigerant made. There's just no comparison.
Great, thanks. We have another question, kind of related. Oscar Nishan is asking, can we retrofit CO2 with R290 and vice versa?
Oh no.
Yeah, so it goes right back to what we were just talking about, piping sizes and compressors and everything else.
Please
But
not.
I won't go with this one. Jorg, you can go ahead, or Christian, you can go ahead and take this one.
No, it's not feasible to retrofit those refrigerants. As you say, the density of the refrigerant are very different. Comparisons, the similar cooling capacity, the CO2 will require a compressor two times less size than the R290. So yeah, density is very different. So pressure is a lot different. R290s are working around 7 bar. And when the CO2 required more than 34, 60 bar.
Yeah, agree. So that that is not possible to go from CO2 to any other refrigerant or the other way around.
And that's a good point, actually.
Yeah, and I think, Jamie, that's one topic, I guess, in future. And I know today we're talking CO2, but I think in the future we're going to have that issue more and more with people retrofitting systems with different refrigerants, and it's something that the trade generally is going to have to be very careful with.
Yeah.
Thanks. Afan Nasir is asking, is it true that a CO2 unit needs more power to run? That's a good one.
Oh,
That's a clear maybe.
yeah. That's
Well,
asking like how
now
far is up, right? You know.
Slightly.
Yeah, because it depends really a lot on the conditions where that system is operating. So if you compare, for example, and I can come back to 513A, to that question we had before, compare that to CO2 regarding efficiency. So let's say you build a bottle cooler and have that bottle cooler standing outdoors at a kiosk. Then CO2 might not be that efficient in the summer because you have high ambient temperatures, and then the total system efficiency, the electricity you need to put into the refrigeration system compared to your refrigeration effect, is probably not that high on CO2 compared to, let's say, 513A. When it's
Is that
very
because it's
warm
working
outside.
transcritical?
Yeah, as soon as you
Yeah.
get transcritical, then you somewhat need more energy. There are possibilities to recover that energy and to make the efficiency pretty good. But in general, as soon as you get transcritical, you don't condense anymore. You have a gas cooler. You need more energy here. However, if you have good conditions, maybe you want to reject the heat at high temperatures because you have a heat pump, or you have a very big temperature difference on your site where you reject the heat or use the heat, then CO2 can be more efficient because you can use that big temperature difference. And other refrigerants get less efficient the higher you get in condensing temperature. So black and white is difficult here. I would never say yes and no.
I would agree.
That in general.
Looking on commercial refrigeration, the test and the number we have on smallest cooling capacity shows that it's with seasonal efficiency, CPR, we are slightly below standard refrigerant. It's just slightly. It's depends how thickness the line you are looking about. If not, it's quite similar. And we are comparing that with our best-in-class inverter systems.
Great.
I guess it's really what you're doing is you got to look at your total energy cost. How much are you spending to heat water or dehumidify the air in the summertime and things like that? And can you use the heat of rejection from a transcritical system? Because a transcritical system gives you tons of high quality heat, very high temperature. There's lots of it. And that's just something you don't get with a typical, refrigerant system where there's actually condensing taking place in the condenser. So it limits how warm and how much heat you can get out of it. There is really not a lot of limitation when it comes to CO2. You get a ton of high quality heat, but do you have a use for it? And so you have to design a system around not just taking heat and dumping it outside. Like the adage for air conditioning is you take heat from a place where you don't want it and you dump it to a place where you don't care about.
Yeah.
Well, that no longer really applies with CO2. If you can have a use for that heat that you normally waste, and it makes absolute sense. It's a crime throwing heat away because it costs money and energy to make it. So if you have that kind of use for that kind of energy, it completely changes the sum of the game then. And so you have to look at it from a whole different light.
Yeah.
Great. Thanks. We are getting a lot of questions, and that's so great because it keeps us talking, keep us awake. We have another one here from Gustavo Moraes. I guess it's Morales. Never mind. Why has Danfoss changed the condenser to aluminum? if possible, please answer in Portuguese. I don't think we have anyone speaking Portuguese here.
No, sorry.
Unfortunately.
What were they made out of before aluminum? Are they talking
Fin-
copper tubing?
Yeah, they're talking fin and tube, I
Yeah, the
guess.
fin and tube.
GAB.
You want me to
Okay.
take that? Or
Yeah,
John, you are?
Christian.
John,
Yeah,
go ahead.
it's
At least we have changed to microchannel exchanger aluminum heat exchanger due to the
Okay.
fact that we have a much better efficiency on the condenser. The delta T inlet and outlet will be maybe 2 times lower. And in terms of efficiency, if you are working at a lower temperature, the compressor work at a lower temperature, it takes less energy with the same pressure to decrease the temperature, then it can bring you 5-10% better cooling capacity. It's a direct impact on your cooling capacity. Meaning we are winning 10% is a lot, is one size of compressor, of small compressor.
Great, thanks. And related, kind of, another question from Mercury Svadshika. Not sure I'm pronouncing that correctly. Do you have any specific plans with Bock?
Yeah, we want to sell them. Do you want to buy a compressor? Yeah, yeah. Here you go. I mean, it's a good question, and I'm currently engaged with large wholesalers here in North America on Bach, and of course our OEM, original equipment manufacturers. Our sales team is obviously currently engaged with them, but it does allow a foothold into new markets for us. It allows us to go into larger sizes. It allows us to go into the traditional markets like supermarkets and things like that and compete. And CO2 plays a big part of this. The box CO2 compressors, you can put a variable speed drive on them. It allows you, all the benefits that you would normally have with the semi-hermetics, and they have a really good program that allows you to service the motors on the compressors without actually having to, completely disassemble the compressor and do a lot of work. So there's advantages there, but that's really a commercial topic outside of CO2. Yes, they work with CO2. Do they work well? Yeah, sure. Right. But I think that's more of a commercial decision on going into the market. You guys want to throw something in on that?
As you said, Bock is a really good part in the Danfoss portfolio. Danfoss did not have semi-hermetic compressors. Danfoss did not have open compressors for mobile applications. Now with Bock in the team, Danfoss can offer all of that, and customers can choose from a really broad compressor portfolio.
Great, thank you. Nassim Aziz has asked, sorry for this, but he's asking what should be the specifications of CO2 as a refrigerant?
Dry.
Less than 10%, I think. 10 parts per million.
Yeah, I was going to say.
Yeah. And then purity is 99.9. So yeah, it needs to be refrigeration grade CO2 for sure.
Yeah, that's the point. I don't have the specification in mind, but please use refrigeration grade. No matter what anybody tells you about the refrigerant they sell, that it's good and great and whatever, as long as it's not refrigeration grade, do not put it into a refrigeration system. Because there is too much humidity, there are too much non-condensable gases and all of that. It has to be refrigerant grade.
I have somewhere on my computer, you guys might have it too, I have a really good image that shows the high and low side temperatures of a CO2 system. And when you get down into the low temp side of a CO2 system, the amount of moisture that you're allowed to have is incredibly low. I'm trying to think of what it is, but it is much less than what you would tolerate in a normal HFC system. So if the refrigerant is wet going in or has moisture in it, then you're going to run into all kinds of issues with plugging on your low side, and that's not something you want to have happen, because then you have to completely open the system up and everything else. So I think that's why I said the word dry a couple of times, because I was very surprised when I saw how dry the refrigerant has to be on the low side.
Hmm.
Great, thanks. Just waiting for the next question. Here we go. That's from Jeremiah Perez. How is recovery affected with CO2? Do I need to recover it, or can I just out in open space?
Mm.
Yeah,
Well, that's
easy question.
an advantage, John. Yeah, you want?
Yeah, I'll take it. Yeah, I mean, you can just let it go to atmosphere. It's a naturally occurring gas, so no issues whatsoever. You just have to be careful when you're venting it that you don't generate dry ice at your exit point within the system. So if you get below 5.2 bar, 5.3 bar, can't quite remember exactly. Yeah, that's when you'll generate dry ice. So you just got to be careful of that.
Great, thanks. Actually have a question myself. Jens is asking, what happens actually? Why are we so scared of CO2 in the atmosphere now? And now you say that we could just let it go. Why?
Okay. Well, yeah, that sounds a bit strange, and that's a really good question, Jens, because we say, we as humans in general, as a human race, we put so much CO2 in the atmosphere that we have this greenhouse effect, and that the Earth becomes warmer and warmer. So we need to avoid that. Good. And then you listen to us talking here, saying, yeah, the CO2 from the refrigeration system, you can put that into the atmosphere, no issue. Doesn't seem to fit, right? That sounds a bit strange. So I fully understand that. It's just when you put that into perspective, how many millions of tons of CO2 we put into the atmosphere by burning fossil fuel, compared to the few kilos that we put into a refrigeration system, then that little bit of these few kilos, they don't really matter.
Maybe we can also think about other refrigerants strategy where we have 1,000. That means each kilo, each gram we resell of other refrigerants are 1,000, 4,000, 2,000 more disturbing the environment. That's what we are reading. So yeah, that's strange to have this I love CO2 strategy, where the CO2 is the global warming potential we are targeting to reduce.
It's not where we get the CO2 to begin with, though. We it's not like we make CO2 per se. We are pulling it out of the atmosphere and refining it, are we not? I'm assuming that's where the CO2 comes from.
And we are reusing something.
Yeah, so that's, obviously there's some energy being used in recovering it, but it's kind of taken out and then putting it back in again. It's not like fossil fuel burning where you're combining masses together, going through the chemical reaction of combustion and producing new CO2 that didn't exist before. So
yeah, I guess you could also say that if we are operating in kilos with CO2, you would be operating in ton when we're talking about other refrigerants, or if we are talking about CO2 from combustion or whatever. So there's a huge difference, and there's no harm in letting the CO2 from a system go. Ashgar Nishan, I think I've sort of taken you a bit up front, where you're asking how is CO2 usage in high ambient countries like India and Pakistan? Sorry, that's about temperatures. Anyone?
Yeah. To be honest, surprisingly strong, in my opinion. At least the interest in using CO2 in India and Pakistan, for example, or other countries where you have high ambient temperature, is surprisingly strong. I did not expect that to grow this fast, the interest here. There is the challenge of the high temperature, the high ambient temperature. However, there are system options to help you to make CO2 suitable even for high ambient temperature countries. A few examples: booster compressors, parallel compression, ejector systems. With these options, you can make CO2 systems quite efficient even in high ambient countries.
Thank you. And yeah, well, it's kind of the same question, I guess. It's Rohit Gupta asking which geographical location is ideal for a CO2 compressor in terms of efficiency.
Mhm.
Arctic,
Not quite the same.
the Arctic,
Yeah.
Yeah.
as for every refrigeration system.
Yeah.
Well, there was the so-called CO2 equator. Years and years ago, that was a bit of a discussion where you had a certain line which limited the useful operation of a CO2 system to more northern regions, or very far south, but there are not too many people there. So to more northern regions where your ambient temperatures are not too high, so that in most of the time of the year you could operate subcritical.
Mhm.
That's how this line was generated, so that you can use subcritical most of the time. That has changed because of these technologies that you have parallel compressors, booster compressors, that you have ejectors, or that you have other ideas how you make the system more efficient. So
Mhm.
now you can use a CO2 system efficiently in many places. Still, it gets more and more efficient the lower your ambient temperature is, but that's the same for R290 HFC ammonia.
Mhm. Any refrigeration system that operates subcritical
Yeah.
is
Great,
in that boat.
thanks. Donovan Van, what pressure do you recommend for running your vessel? 37 to 48 bars? Does running a higher vessel pressure make any difference?
We probably talk about the intermediate pressure vessel here. When you come from the gas cooler,
The
have
flash
your
gas.
high pressure valve, and then expand
Yeah,
the
okay.
gas
Yeah.
into that intermediate pressure vessel. Um, there is not one single value, but just as an idea, typical operating temperatures, and here we have the direct relation again between temperature and pressure, but quite often these vessels have a temperature of approximately 0 degrees to 5 degrees Celsius, something like that, which corresponds on CO2. And now I need to do a short calculation. Sorry. Maybe somebody
Carry
is
the
faster
one.
than me. Here we go, which corresponds to a pressure of 34 to approximately 38 bar. That's where most of the systems operate.
Okay.
You can run that on a higher pressure. That has certain advantages, certain disadvantages. If you do that on a higher pressure, then you might run into the challenge that you don't have enough pressure difference from your gas cooler to that intermediate vessel in case of subcritical operation. It just depends a bit on the system setup. So I don't see one single value there.
Mhm.
I would probably say, Jorg, it's more the difference between your evaporating temperature, pressure, and your vessel pressure, temperature.
That's
I think that's
another
what we need
big
to talk
point.
about.
Yeah.
Is that pressure difference? And yeah, I mean, you're talking again roughly, because not every system is exactly the same, but 25 to 30 bar difference between your evaporating pressure and your vessel pressure. So your intermediate pressure is there or thereabouts where you're going to get the best COP. is at least my understanding.
This is how we maintain the COP.
Yes, correct. Yeah.
Great, thank you. Kunal Patel is asking, what's your take on control philosophy for transcritical racks for high ambient places to get maximum efficiency from the system?
I guess that sort of comes back to what we were just talking about, Jens, is that pressure difference between your evaporating temperature and your vessel pressure, and then controlling that with your gas cooler. To try and keep that level so you maintain your COP.
That's an interesting point. And if you go to real big systems where you can afford to install some more control equipment, then we talk again about ejectors, which recover some of the energy that you kind of lose when you expand the refrigerant from gas cooler pressure down to intermediate pressure.
Yeah, the bigger the system, the more impact they have. If I remember correctly.
Yeah, and the more you can afford them. So if you have a condensing unit of 5 kilowatts, you wouldn't put them in. They are just too expensive.
Yeah. Now, how does heat reclaim, if you had a use for that high temperature heat, how much of an impact would that have on your parameters? Does it open up a way of operating your high side or your racks differently than you would if you didn't have a use for that heat, if you're just trying to maintain your best COP without any use for that high side heat?
Yes, it does.
Okay.
So what you do is you maybe sacrifice a little, or not maybe, but you go a little bit higher in your gas cooler pressure to recover that heat. And you go to a point where your efficiency is lower as if you would not recover the heat. So you sacrifice some efficiency on the cooling side to be able to recover that heat. But in total, you get more. Example, you have 100 kilowatts cooling, and let's say you would have 30 kilowatts electricity, and then you get a heat load out of that of 130 kilowatts in theory as a maximum. Now, if you want to earn or harvest, not earn, but harvest that heat, you make your efficiency a little bit lower. So maybe instead of adding 35 kilowatts of electric power, you now 30 kilowatts of electric power, you now add 35. So you add 5 kilowatts more electric power for your 100 kilowatts of cooling, which lowers your efficiency. But all of a sudden, you have the possibility to get 130 kilowatts of heat out of that, which you did not have before. You can get the complete heat out of it. So your earnings are 100 kilowatts cooling plus 130 kilowatts of heating for adding an extra 5 kilowatts. That's pretty good, right?
Yeah, that I think, kind of nails it going forward as we want to electrify everything. And that includes, getting every ounce of energy or performance out of a system. If you can heat your hot water and store it, if you can heat your buildings in the wintertime, if you can reheat your air that you're dehumidifying so you can keep your supermarkets warmer without having to worry about condensation taking place on the floors, things like that. I think there's a lot of opportunities, but it's a much bigger picture that we're looking at compared to the old, I need 10 tons of cooling, and this is a system I'm going to put in, and I want it to be as efficient as possible. So it adds a whole other thing you need to look at when we're looking at installing these big systems.
Great, thanks. Nassim Aziz asks, can we use plate heat exchangers as condensers in CO2 systems?
Basically, yes, of course, you need to have a plate heat exchanger which is approved for these pressures there.
Meaning 140 bar.
If you run it transcritical, yeah. If you of course have water or anything else that's all the time very cold, you can stay subcritical. You need to have a plate heat exchanger that's approved for CO2 and for the pressures you have there. But basically, it's possible, yeah.
Yeah, great, thanks. Mert Killis is asking, can another refrigerant gas be used in supermarkets instead of CO2 in future? Is there a refrigerant that you think will replace CO2 in the future? That's a good question.
Oh, yeah.
That's a bit of a challenge, because let's go through the refrigerants, and maybe that answers why CO2 is used so much. I mean, we had F gases. They have a high global warming potential. So we want to get rid of that. Let's look into something else. Ammonia has a low global warming potential. If you have a leak, you don't want to have ammonia in the supermarket where your customers are. That's a panic refrigerant. You don't want that. So it's out. Then we have, what else do we have left? We have propane left. If there's a leak, you get a lot of propane into the supermarket with all your customers in the supermarket as a direct evaporation. Probably not. Yeah, and that's it. What we have left. I don't have any other ideas. I mean, we could use nitrogen as a gas direct, but then CO2 is even better than that.
Yeah.
How about water?
Well, yeah, but water, you need to have a chiller to cool it down. You can pump water into the supermarket. That can be done, and that is done already, or brine. But of course, you need then a refrigeration system to cool it down. Direct evaporation of water requires very big compressors, and on the long pipes, a huge volume. You have very big pipes. That makes no sense as direct evaporation.
Instead of low pressure, low density. Yeah.
We don't have a large choice of molecules in the world to change that. I think that further than that, changing the refrigerant, the strategy how to cool down those refrigerants, or how to condensate, or how to modify the status or the stage of the refrigerant might be a way better to see. Or the strategy. We change the strategy of refrigeration. We don't have fresh product, maybe only frozen product. We only use fermented product. Fermented product can be used and can be kept at standard ambient temperature. But I'm going too far, maybe.
But thank you anyway. Dinesh Yadav, how efficient is CO2 in high ambient conditions like India, and what is the ideal COP in such conditions? We touched on that earlier, but can you elaborate?
Who wants? Okay.
Yeah.
Well, how efficient? I don't have a number now. I cannot tell you this is the best CO2 you can COP you can ever get. So I cannot give you a number, because that depends on what you do with that system. Is it a heat pump? Is it something that cools medium temperature down? Is it something that you use for low temperature? That has a major influence on that. As mentioned before, there are quite some applications where you have a higher efficiency with HFCs in India, for example, or with propane. You can come close to these efficiencies when you put some additional stuff into the CO2 system, like ejectors. If you do heat recovery as well, in case you need heat recovery, let's say to warm up sanitary hot water, then your CO2 system gets more efficient, because you do not need anything else, any other heat source
There you go.
to heat up your sanitary hot water. It's then a complete energy view. It really depends on what you do.
Yeah.
Yeah. Thank you so much. I think we'll jump to Deepak Rai. He's asking, does the high power consumption with CO2 as a refrigerant justify the specific heat capacity of CO2?
Yeah, I mean that's again, you got to define high power consumption. What is causing your high power consumption? If it's in a subcritical state, then it's not high power consumption, because again, you got to look at your COP, how much net refrigeration effect you're getting for the amount of energy you put in. And as Jorg says, if it's a transcritical system, you have to look at all the variables. Do you have a use for that energy? You know, what would you pay normally for the energy that you would be using in your transcritical system? Is it part of a two-stage system? All of these things you have to look at together. There is no one solution, no one answer to that. It's going to vary based on your application, the use that you have for the surplus heat, and what your ambient conditions are going to be. But majority of the time when you design a system like that, you're taking the best solution. And so, yes, it definitely justifies that in the case that your specific heat's higher and you have a use for the extra heat. Overall, you come out on top in the energy equation. That's what it kind of comes down to.
Yeah, we have a lot of question coming in.
Yeah, let's
I'm
see if we can
afraid.
get one that's kind of touching on a topic that we haven't already touched on here.
Yeah, that is a good one. I think, yeah, there's a good one here. I hope it's a good question that we have here from Stephen Benton. Is EEV different and important versus flash gas forming in the liquid line?
They're two different things. Liquid forming in your flash gas is going to affect any metering device. And an electronic expansion valve has traditionally been used in CO2 systems, although there are some mechanical TXVs that are coming out. But I'm not sure what the relationship is that he's asking there.
I mean, generally, if you talk about your metering device, Jamie, as you said, traditionally within, let's say, the food retail environment, we've used EEV or AKV.
Mm-hmm.
If you know you have flash gas in the liquid element, then you would, let's say, oversize your AKV to cope with that challenge of having flash gas in there. So I guess, Stephen, it depends on the percentage of flash gas that you've got as to how you would size your metering device, whether it's AKV, whether it's stepper, whether it is TV.
Oh, okay. I just see he's actually updated. I was answering the question as to why the intermediate pressure was as it is.
Okay.
Okay.
Was not checking.
Right. Okay.
Sorry about that. We missed it.
Okay. All right.
We have another question that is about this system and racks. Let's see. How many racks? Oh, sorry. It's Jose Alberto Ortiga Torres. He's asking how many racks or tanks per loop. Could you clarify this a bit more?
Oh, man.
I guess, is he meaning about how many evaporators on a system, or?
That's a pretty specific design question, actually.
Yeah, depends on the size of the rack and pack.
Yeah, I agree, and maybe the idea or maybe the question goes towards: do you need several intermediate pressure vessels in one system? If that's the question, no, you can have one compressor rack and connect that to an intermediate pressure vessel. You can even connect two compressor racks to that, a low temperature and a medium temperature compressor rack. They can work on the same intermediate pressure vessel. That's possible. And per rack, per compressor rack, let's say on a low temperature rack, you can of course connect quite many different evaporators on a large system. That is possible as well. So you do not need to have two pressure vessels. at different intermediate pressures in a system that can do low temperature and high temperature together.
Great, thank you, Jorg. We have another question from Ashkar Nishan Malik. He's asking, does transcritical CO2 require specialized components for handling the increased pressure? Yeah.
Yeah.
Yep. Generally, yeah, your system, the components within the system have to be able to withstand the pressure that you're working at. So typically, let's say on a commercial condenser unit CO2, your gas cooler would be 140 bar, and then you'd have a 880 bar in the rest of the system. So they are specialized because they're made to do a job and work with CO2.
Mm-hmm.
At these high pressures.
Yes. Yeah, and then obviously standstill pressure as well. So yeah, making sure that everything is at least 80 bar to cope with a standstill pressure.
Jose Alberto Ortiga Torres is back again with another question regarding the transcritical operations. What to do when the ambient temperature exceeds the 30 degrees Celsius with the problem of transcritical CO2? The expansion valve has to be electronic for these equipments or not? I guess it has to do with the intermediate.
I think we kind of beat this one to death, but you guys want to just do a quick overview on this again?
Yeah, I mean, you're taking your liquid from your intermediate vessel, which your gas cooler is cooling your CO2. You take it through the pressure reduction into your receiver. So whether it's transcritical or subcritical, it doesn't matter. You can use
not for the expansion valve ahead of the evaporator, because as you say, John, that gets the liquid from the intermediate pressure vessel, and then you can use thermostatic or electric expansion valves. However, until recently there was no thermostatic CO2 valve on the market. Now there is the T2 from Danfoss. But if we talk about the valve which is after the gas cooler,
maybe yes,
that makes a lot of sense when that is electric, because then you can adapt to this change. Your system might run subcritical in the winter, and then summertime comes, the system goes transcritical, and you can adapt that valve. You control.
It becomes a gas expander then, and
yes. Yeah. That's maybe what he's talking about. Yeah, quite correct.
I'm sorry, but we are sort of slowly closing in on an hour now. Wow. Yeah, but the question keeps pouring in, and for you out there, we'll try to answer the questions afterwards. So if we haven't answered your questions here live directly, then please take a look a few days later, and we should hopefully be able to answer, if not all, then at least most of the questions that we've gotten today. But let's just take another one here. It's from Amar Risik. Yeah. Where do you position yourself or your own CO2 portfolio against HFO? That's the Danfoss portfolio, I presume.
In parallel, I would say.
Yeah.
Danfoss offers components for all refrigerants.
At the same cooling capacity, similar cooling capacity.
Yeah.
Yeah.
So not much discussion on that one.
Yeah, I mean, if you're, I'm asking if one is better than the other or what we're banking on for the future. Well, we don't know. We're not fortune tellers. So, we basically offer whatever the market demands. And, right now, both options are on the table and both of them work together. I mean, as Jorg has mentioned a couple of times, a lot of times HFOs or HFCs are part of a system that also includes CO2. I saw a
But
question on the line there where they were talking about CO2 and ammonia, and that's a really, really good question actually on two-stage systems. Again, it all depends on the advantages and what the market demands and what are the benefits coming from, savings on other side of the system. So
A question from Rick Nassif. It looks like he's in New York. How does the CO2 system work in comparison to other refrigerants in the central New York area?
well,
That's a
New York
great
State,
question.
if he's talking about,
Sure.
that's kind of an environment where you're going to run six months of the year subcritical, and probably 6 months of the year you're probably going to be spending a lot of time in the transcritical. So it's the same as any other type of climate. You got to look at your energy costs and what the applications are and whether you have a use for that heat. And New York's a relatively progressive state when it comes to energy in that sense in some ways. So if they have lots of domestic hot water or hot water usage for the waste heat in the transcritical times, it makes a huge plus. So from that standpoint, it's going to operate better than, say, an HFC or HFO system. But if it's going to be operating less efficient during the transcritical times and you don't have a use for that energy, then it becomes much more complicated. But that's no different than any other place where it's has a similar climate.
Good. Thank you. Manuel Pereira has a question. Can we start exchanging the copper heat exchanger for aluminum for more heat transference and thus performance?
I think we answered that one already with micro heat exchangers, and the answer is yes, absolutely. Micro heat exchanger has a lot of advantages of running closer approach temperatures, lower refrigerant charges, and things like that. It's a little bit more complicated to make, but yeah, I mean, if it's from an energy transfer standpoint, then yes, it makes a lot of sense, and we are introducing them in our condensing units.
Right. Sharafkan Sajid asks, are existing CO2 systems enough or we must replace with new already now? I presume it's about renewing an old CO2 system.
Well, I would say that's the same as we had that with HFC systems.
Mm-hmm.
If you have a CO2 system that's working, that's 10 years old, you can still operate that for some time. If you have a system that's nowadays, there are a few already towards 20 years old and older, it might be a good idea to think about replacing that one because you get a new system with more modern components, with more efficient system setup and components. I don't see a difference to other refrigerants here. It's the normal life cycle.
Yeah, great, thanks. Ashka Nishan Malik is asking, and I think that's about the last question, I presume. How about usage of CO2 in transport refrigeration?
That's
What do you think,
the
guys?
question between flammable refrigerants, standard refrigerant, and CO2. We have flammability in certain refrigeration system, so it may affect the safety of the person. And on the other side, with CO2, we have more pressure, so it can affect and damage in another way. It's not a clear response.
Yeah, but I mean, there are systems in CO2 in transport, or for example, bus and train air conditioning or railway air conditioning. That they are already there. They exist. Not necessarily the majority yet, but they exist. So you can use CO2 there as well. It's again a question of what are your parameters? Where is your focus? Is that an advantage for you or not? That's always the same question. That's always a decision you need to take when you build such a system. What is your focus parameter? There is no refrigerant which is the best in any parameter. That does not exist.
Great, thanks. I take the pleasure of asking the last question for today. And then, as I said before, take a look back in a few days. We may have answered your questions in the chat. We just need some time to do so. We'll take the last question from Matthias Emanuel Bauer. What do you think about the cascade systems with CO2 and NH3?
Ammonia. I like this one.
Yeah.
I had the pleasure of actually back in the day taking my CO2 training at an ammonia training center down in the US. And a big part of the focus was integrating CO2 with ammonia and what are the benefits and when and why would you use something like that. On the surface, ammonia is a fantastic refrigerant. I mean, it has a ability to absorb heat, per weight of refrigerant far greater than anything else, even water. But it also has its limitations, as Jorg mentioned before. It's toxic. If you have a leak, you'll know you always have a leak because you can smell it. It's a strong irritant to the respiratory system, and on and on and on. On the other side of things, you have a situation where if in some countries, if your ammonia charge exceeds a certain amount, you have to pay licensing fees or special considerations or special permits. You might need special qualified people on site, things like that. Also, if you have to pump refrigerant out into remote areas of the system of the area, it's much easier to pump CO2 than it is to pump ammonia out into these places. So all this stuff is taken together. On paper, if you have an ammonia high side, in other words, your high temperature half of the system is ammonia, the low temp side of the system is CO2, you require very, very, very close approach temperatures. In other words, the difference between your CO2 and your ammonia has to be very fine, which means you need very large heat exchangers. That rule applies the higher your low temperature side is. But once you get down below about minus 30, 35 Celsius, minus 30 Fahrenheit, suddenly the efficiency of CO2 starts to take off. And then it starts to make more sense from a efficiency standpoint to utilize CO2 on the low side. But again, it's not just an efficiency standpoint. It's also what are these other benefits of using CO2? There's much lower ammonia charges. There could be legislations and licensing benefits to that. All of these things play together. But it really comes to pass when there are reasons using ammonia has a negative other than efficiency. That's when CO2 starts to shine on that side of things. I hope that answers your question.
Yeah, thank you so much. I will, on behalf of myself and all our experts here, say thank you for attending this live stream, and we'll be back again, I'm sure. This has been quite interesting. We've had a lot of questions, and I'm sorry to say
this has been crazy, man. We could go for hours. It's nuts.
We could, yeah, but we won't today. Yeah, I'm sure we will have another session another day, and yeah, thank you so much, and have a nice rest of the day or evening or wherever you are in the world. Bye for now.
Good morning here.
Yeah.
Morning, evening.